Good morning, everyone. It's great to be here and to talk to you a little bit about regional environmental flow assessment. My name is Rebecca Thalm. I'm with the Nature Conservancy's Global Freshwater team, and I'll be presenting on behalf of myself and my co-author, Eloise Kendi, this morning. I'm really going to be talking about how to scale up environmental flow thinking from the level of site or project level determination to determining environmental flows across much larger spatial scales, whether it's a large river basin or a region as large as, for example, a state in the United States. So I'm going to start by just giving a little bit of context in terms of the rationale for why we might want to address environmental flows at the regional scale. I'm then going to talk through the basic components of the framework for setting environmental flows at the scale, or the Ecological Limits of Hydrologic Alteration framework. And then I'll try and work through some of the steps of ELOHA with some illustrative case study materials, bearing in mind that this is a fairly new approach, so the number of case studies to date is fairly limited at this stage. So just to recap, you've heard a great deal already in the course about local scale environmental flows, how to really approach this issue when you're assessing environmental flows for a section of a river or a number of tributaries and a main stem of river, and particularly for individual projects, for example, a large hydropower dam or a big water storage dam for irrigation. I'm now going to be talking at the regional scale, so really scaling up from that level to a basin or a wider scale. So in terms of why might we want to think about doing this? Well, this is an illustration from the United States of all the places in the US where environmental flow prescriptions have been made to date and where they've started to become implemented. And you can see that there's a wide range of river types for which environmental flows have been determined across the breadth of the country. However, these are all the rivers for which environmental flows have not been prescribed or implemented thus far. So we can see that for more than 80-odd%, even 90% of the rivers of the United States have not had environmental flows put in place yet. So we really need to find a way of setting environmental flows more rapidly across big geographies, to be proactive about flow protection in places where we have high priority systems, where we need to really maintain rivers in a healthy condition. Oh, gosh. So this brings us to thinking about ELOHA. And a few years ago, a group of scientists from a number of institutions across the world got together to address this issue, to see whether they could really think of a way of scaling up the information, the knowledge, and the processes that we've been using for many years now at the site level, and how we could really develop those and use them at a different scale. For a long time, there really wasn't enough information to be able to achieve this. But in 2010, a group of scientists from a number of different organizations were able to publish the first approach to really do this. And the reason is that we really, to assess environmental flows at the site levels is very expensive. It requires a lot of time and resources to do it at a one-on-one for all the different rivers. But there wasn't really a scientifically credible approach to scale up that site-specific knowledge to a regional level. So this framework allows us to actually do that. So what does a regional environmental flow method need to be able to do? What does it need to have in terms of criteria? It obviously has to address many rivers simultaneously. We're trying to scale up from individual rivers. It has to be able to address many rivers of different kinds at the same time. It has to explicitly link flow and ecology in much the same way as a site-level environmental flow method might have to do. And it needs to obviously be applicable across a spectrum of flow types, flow alteration types, a range of contexts in terms of the availability of data and technical capacity, and of course a breadth of social and political contexts. So quite a tall order in terms of what we would need an approach at this scale to be able to handle. So the ELOHA framework tries to address this by having two components that are very closely interrelated. The first is a scientific process, and that is complemented by the social process, which really brings in the stakeholder engagement and information on what desired future state is wanted for rivers at this larger scale. And what's very important, I think, to note is, although here it's portrayed as a scientific process and a social process, one alongside the other, they're not necessarily, they will be running in parallel, but they will be highly integrated. There will be particular places where the social process is very strongly connected with the process of actually determining the environmental flows through a science-based approach. And one might think of the scientific determination as really being nested within a social process, rather than one following the other, or more than running sort of isolated in parallel. And I will work through both of these parts of the process with some illustrated case materials. But essentially, you can see that the science process has a number of steps. First step being the development of a hydrologic foundation. The second step being around stream classification, classifying rivers according to their type. The third step is around understanding flow alteration. And here, of course, it's flow alteration across rivers within a type, rather than flow alteration on a site-by-site level. The fourth step is about developing the relationships between flow and ecology, and flow alteration and ecological response. And then the social process really brings in the societal values management needs into the thinking, looks at what are acceptable degrees of condition to maintain rivers of certain types in, and then really that is the stage at which the environmental flow standards are actually established and implemented. And in much the ways one would think about it at a site level, this is an adaptive management cycle, cyclical process. The key to ecological limits of hydrologic alteration is in many ways very well aligned with the principles of environmental flows at the site level. So really, essentially, we're looking at gradients in ecological condition across rivers within any one river type in a river basin or in a large region, and gradients of hydrologic alteration. So along the x-axis, we have here increasing hydrologic alteration, and on the y-axis, ecological condition, ranging from, at the top level, rivers that are in excellent condition through good, fair, to poor. And one can simply think about, as we increase hydrologic alteration, we have a lot of evidence to show that we can expect to have a decrease or a decline in ecological condition. And the interesting thing to bear in mind is that the relationship between alteration and ecological condition can take a number of forms. We can, for example, in A, see that it's a fairly linear relationship. As alteration increases, there's a fairly consistent decline in condition over time. However, we may have cases with particular types of rivers or particular parts of the ecosystem where the response is very different, where there doesn't seem to be much change in condition for some time, for example, in relationship B, but then very suddenly we have a severe or abrupt change in ecological condition from very good condition to a far more degraded state. So we have to bear in mind that the nature of the relationship may be very different for rivers of different types and for different flow indices or different components of the ecosystem. And so the principle is really that we can usually manage through environmental flows. We can manage the flow regime, which is a lot easier in effect to manage than managing the ecological condition itself. So that's the basis of the foundation of the thinking conceptually. If we look at the scientific process of how do we actually establish environmental flow standards at this broader scale, we'll start by looking at the hydrologic foundation. So what does that really entail? What do we have to understand at this bigger scale in order to be able to understand flow condition and alteration of that flow condition? And we can think about the hydrologic foundation as really the core of decision support around basin flow management. And here we have, at its core, we have in the center typically a hydrologic model of the and it's usually operating at the basin scale. And this may be models that are already in use by water resource agencies such as Mike Basin or maybe linked to weak modeling. So there will be various models that are used typically in water resource management that will be part of the hydrologic foundation. We also need to have a stream flow database. We need to know what information is available on stream flow time series or hydrologic time series. And we need to note that for two reasons. We have to have some understanding of the baseline hydrographs, the observed data on baseline condition, preferably including pre-development state. So some description of what the flow regime looked like at different places in the basin, naturally or before major alteration. In some cases, that information may not be measured. It may need to be simulated because it doesn't exist, or the record simply isn't long enough to cover what we might expect to reflect natural or other baseline conditions. We also need to have information on this side of the foundation. We need to know something about developed conditions. So what are the stream flow time series looking like with development? Whether that's whether it's different kinds of infrastructure that have been put in place, such as dams or diversion systems, whether it's gradual withdrawals of water over time, or land use land cover changes that start to affect the flow regime and start to alter flows at different places in the basin. So we need both the baseline and we need the developed condition hydrological information. We obviously need to have a lot of background information on basin characteristics. We need to know something about climate, rainfall, temperature, perhaps projections of climate change and other kinds of characteristics of the basin. We need to know something about water use, how much water is currently taken off by different sectors within the region that we're assessing environmental flows for. So we need to really have as good a database of water use as possible to use in this process. And we can then model the baseline and the developed condition hydrographs for various control points in the region that we're looking at. And if you think about the region as a large basin, we may have different points within the basin where we need to be able to manage flows in a more sustainable and a more environmentally healthy way. And we will identify those various points in the basin, and those will be the control points where we really need to understand what is the current alteration, what was the natural condition, and so we can get a sense of what is the gradient of flow alteration at that particular location. What do we do with the baseline information? Well, the next step really is about classifying the rivers into different types, and for that we use the information on what is the natural flow patterns of rivers within to find out how many different types of rivers we might actually be dealing with in this particular basin. And so we use the natural baseline hydrographs to develop our understanding through classification, and I'll go on to show a little bit more about that. And we use the comparison between the baseline and the developed hydrological time series, obviously to show how much flow alteration those rivers have experienced across the different flow times. Because ultimately we are interested in understanding gradients of flow alteration and gradients of ecological response within any one type of river system within the basin, rather than for any one site. I won't talk about any of these specifically, but there are a number of hydrologic foundations in existence. These are some examples from the United States. These are various decision support tools that provide the hydrological basis for doing environmental flows using ELOHA. They have a variety of forms, but many of them are online, structured in an online way, computer-based decision support way, which makes it very useful to use them within this process. So one can go and look at any one of these kinds of tools, all slightly different in their structure, but with the same general purpose for this process. So that's really the Hydrologic Foundation in its basic form, and you can certainly read more about the details of what is behind that foundation in the reading materials that you have. So as I said, we'll use the baseline hydrological material to actually do a stream classification. And I'm going to now just talk a little bit about stream hydrologic classification. This is an example from the United States, from Michigan. It's a river classification that was done taking all of the stream flow time series of natural condition across the entire state in this case. So it's hydrological time series reflecting all the different streams and rivers within that basin for which hydrological data was available or was simulated because it was needed. This one is hydrology based, and we can see that there are a number of different kinds of flow types, river flow types within the basin. For example, we might have a groundwater. One kind of flow type might be groundwater driven with a very high base flow regime. So it's very much influenced by local groundwater conditions. We may have other river types that are very much rainfall rainfall driven or runoff driven, and they may be very much more variable in their pattern of flows over time. So we can think about the differences we may all know among rivers of different kinds in different parts of the world. We can think, well, within a basin, one might also expect to find a number of different types of rivers. In this case, it's about 11 different types of rivers that were classified successfully within Michigan. And the important thing to note is not only are there a number of very different types with very different hydrological characteristics, but then they're not spatially continuous, obviously. So we may find upper headwater streams with very variable flows located across the basin under certain kinds of conditions. So rivers of different types are not going to be necessarily grouped together within the basin, and that's an important thing to bear in mind. I want to talk about a more recent example. This is an ELOHA, so that's an ELOHA case from the US, which is well advanced. I'll talk about one that's underway at the moment in Colombia, in the Magdalena Basin. It's the largest and most strategically important water resource basin in Colombia. A large proportion of the population reside in this basin. And we're in the process of starting to use ELOHA to develop environmental flow standards for this entire river basin. And so we started with thinking about how will we classify rivers of different types. This is a very heterogeneous basin in Latin America. And the challenge was, well, it turns out to be one of the most heterogeneous, diverse basins in the whole of Latin America based on other work that's been done. So the challenge would be, well, what criteria to use to classify it? And it was decided in discussion with ecologists and people who know the basin very well that a purely hydrology-based approach to classification wouldn't work so well in this basin, that we needed to bring in some other basin characteristics to help refine that classification and make it more ecologically relevant. So we're looking for river types that are defined in terms of the hydrologic pattern, because we know we can assume an association with ecological response. But we want to make sure that we can make that connection with ecological response. And so after a lot of discussion, it was agreed that elevation or altitude was a very good surrogate for temperature changes across this basin and a very good way of improving and strengthening the classification. So included the information on elevation and indirectly, therefore, some of the changes in temperature, in addition to information on hydrology. This is so we added indices of hydrology. Now we ran an analysis to generate a number of ecologically relevant flow indices to characterize the hydrological regime, as you had explained in some of the earlier materials. And we linked that with information on elevation. And through various multivariate statistical techniques, we could actually classify the rivers into a number of types. And it's a process, of course, it's an iterative process of looking for the strongest, most useful classification. It's not simply a straightforward classification process. You really need to think about the application of that classification. So using various hydrological multivariate statistic analysis and including some other variables, we were able to start to see that we had very different kinds of types of rivers across this basin. So we had a number of types, and I won't go into the detail on those types, but you can see type 3 has a very different general pattern of flow over the year. This is discharge on the y-axis and months of the year on the x-axis. And we can see that in different parts of the basin, we can have very different looking patterns, general patterns of flow. And this is really at the basis of the classification. And going more deeply, we can then use all of the information. This is the GIS-based information that we had on stream flow gauging network, where it was located in the basin. This is the results of the analysis. We had at first about 24 different types of rivers across the basin. Now, in reality, there probably are a very wide range of river types, and 24 might be a really good number for displaying the entire variability. But from a management perspective, or from an environmental flow standard setting perspective, it's going to be very hard to set environmental flows for 24 different types of rivers. One can imagine just trying to understand ecological response relationships for any one of those types is a challenging enough process. So we had a lot of discussion, and we looked at what ways could we practically consolidate down this number of river types and still have an ecologically useful set with which to work. And we eventually came down to the idea of developing effectively a family of river types. So we had six basic families of river types for this basin, ranging from, for example, the Páramo or high altitude grassland river type, right through to river floodplain river types. And in some cases, there is really only one type of river within this family. So there will be one subfamily of Páramo. In this case, we had only seven time series to describe that. So we had 7 separate places in the river basin where we had streamflow time series for Páramo, natural streamflow time series we could use to class it. In other cases, we had far higher number of time series for any one of the families. So we have greater and lesser confidence in the characterization of these different river types. But we felt pretty confident in these 6. And if we think about them simply, these first few river types here, these first 4, we can think about in terms of 3 basic characteristics. Very simply, as you go further and further along this family, we get an increase in the average discharge as one of the flow indices that was meaningful in separating out these different river types. You can also think in the Páramo we had a very high number of reversals in flow, so we had a very high degree of flow variability. Whereas as you go further along into these other river types, we have far more gradual changes in flow, far less within your variability. And also, of course, elevation played a key role. For 2 of the river types, they really are on the lower mountains and floodplain areas. So very distinctly different based on elevation as well. So then we could work with those flow types and say, for these river types, we can set environmental flow standards per type of river within this whole large basin of the Magdalena. So that's a little bit about classification of river types. There's a great deal of information on how to classify using hydrologic data, and some very good examples, for example, in Australia at the continental scale of how to do it using hydrology, how to do it using other characteristics, and how to bring those 2 classifications together and look for the commonalities or areas of difference within them. So there are a number of ways in which one can approach this. In some cases, we may want to do some refinement. We may know that geomorphology plays a critical role in differentiating the types of rivers we have. For example, we are working on it with an application of ELOHA in the south of Mexico, in Chiapas, Pacific coast. And there's a very distinct gradient between the mountain areas and the rivers within them and then the coastal plains. It's a very abrupt change geomorphologically. And so we may want to think about subclassification. And one way, and this is an example from the United States where they used hydrology at the top of the screen. They used hydrology, they used stream elevation as well. They also used some simple criteria such as the size of stream. So they used size of stream as one of the measures for the classification. And they looked at things like gradient and geology as well to get a more refined classification. So they came up with quite a sophisticated classification based primarily on hydrology and then refined with geomorphological characteristics. Once we've got an understanding of what the river types are, then we can move on to thinking about, well, those river types are the types we would understand based on their natural flow patterns or their baseline flow if there was a decision to use another baseline other than natural. We can start to think about, well, that's good at understanding the river types, but how do we understand flow alteration? And that process is very much the way we would do it for a site level assessment, except that we're calculating hydrologic alteration across multiple rivers within any one time. And then we can see that there might be differences among river types in terms of how altered they are and in what characteristics of the flow regime they are more or less altered. So when we start to think about that, we obviously need to look very closely at what variables we use to describe alteration. We might be thinking, again, we might be wanting to have variables that are very strongly linked to ecological conditions. The more mechanistic or the more directly we can make the connection between flow indices and their alteration, ecology and ecological response, the better chance we have of developing strong, robust relationships on flow alteration and ecological response. So that really is an essential feature. We can classify rivers into types using a number of hydrologic indices that may be less ecologically relevant. But the more we can narrow down to the more ecologically relevant indices, the easier it becomes to actually set environmental flows. We also want to try and have some hydrologic indices that we use that are amenable for use as water management targets. And I'll show you an example towards the end of the median August base flow was actually used as a flow index for setting the flow standards. We really want to use as much as possible indices that managers can work with, understand, relate to, and be able to manage with. And these are just some examples of indices that might be useful in terms of strong links to ecological condition or useful as water management targets. So for hydrologic alteration, we would, again, in much the same way as we would do it at the site level for an individual river, we would start to look at comparing the natural stream flow time series with the altered stream flow time series for all of the rivers within each type, using various kinds of tools that are available. The indicators of hydrologic alteration is one freely available set of software to do this, but one could imagine using a number of other tools to generate flow statistics. What's nice about the indicators of hydrologic alteration is it has a number of indicators that are more general hydrologic indices, and then a number which are very closely linked to the derived for ecological flow components. And as you will remember from other lectures, we can think about breaking up the flow regime into ecologically relevant flow components, whether it's extreme low flows, small floods, high flows, and so on. And for each of those, we can use indices that characterize the magnitude of those flow components, their timing, duration, and so on. So very much the same way we would think about it at the individual site level. And we can use indicators of hydrologic alteration to then compute hydrologic alteration river by river within each flow type in the same way. And here's an example for the magnitude of small floods for a particular river, which will be within a certain river type. And we can see here we've got discharge on the y-axis in cubic feet per second in this case. And on the bottom axis, we've got the stream flow time series. The red is the period before alteration. The green is the time series after alteration. And bear in mind, remember here we're talking about magnitude of small flood. So one ecological flow component, one hydrologic measure that we're looking at. And we can see a very clear difference between the before and after, in this case, infrastructure development. And we can do that same kind of comparative analysis to see how much alteration there's been using a number of indices for each of the rivers. And this way we can start to build up a picture of alteration across the basin. Here's an example from the Fraser River Basin in Colorado. There's the rivers on the far side on the map. And if we look at them in terms of the degree of alteration, each of those kinds of rivers, we can see that they are differently altered. They are altered to different degrees and in terms of different kinds of flow indices. So, for example, the Fraser River in the black solid bar shows extreme low flow duration. So we can say that Fraser River has been subject to a high degree of flow alteration in its very low flow, in its natural low flow component. And that is more pronounced in that river than in some of the other rivers. And probably, I don't work in this basin, but if one looks at the map, there's a lot of upstream diversions on some of the tributaries, and we can expect that those withdrawals have been affecting the low flow part of the flow regime. So we can start to see that different rivers in the basin will be having different degrees of alteration, different ways in which they're responding to that alteration, and we can characterize them using a number of ecologically relevant flow metrics. So we can start to build up a picture then by flow type of the ways in which they're altered. For example, here we're looking at two different types of river types, and they are geomorphologically subclassified as well, so we can see where they are spatially located within the river basin. And for example, the headwater type, we can see that overall, across this river type, there's been alteration in the extreme low flow duration, and it's been in the order of 26% increase. So there's an increase in the duration of very, very low flows in this headwater type stream within this basin. Similarly, we could look at large river floodplain types. There may be fewer. Typically, you would expect to find fewer large river floodplain types within the basin. And in this case, we can see that the indices that have changed are different in much the same way as they were within the Fraser river system. So it's different indices that have changed and to different degrees. In this case, with a large river floodplain type, one of the more important changes has been in relation to the frequency of large floods. In the headwater type, large flood frequency had changed very little, -4%. It had a decrease, but really by a small amount. However, in the large river floodplain type, large flood frequencies decreased by 81%. There's been a massive change in the frequency of large floods for a type of river that the ecologists can start to say something about. Well, it's a large river floodplain type system. We can expect the ecology to be very tuned to the flood pulse. And we know that this system has a gradient of alteration around one of those key indicators, flood frequency. So that we start to build up this picture of hydrologic alteration by type across the basin in this kind of way. That leads us on to the step about flow ecology relationships. And here, if you remember, it's the core of the ELOHA is really thinking about gradients of hydrologic alteration and the gradient of ecological response. One of the important things with ELOHA is it actually takes existing empirical information or existing expert information across the basin. It starts by looking at the basic understanding that ecologists and others have in the basin about the relationships between flow and ecology, and then it looks for where is the empirical information existing. And because we're dealing with multiple rivers within any one flow type, we have multiple sources of data within a flow type. So we're able to generate potentially stronger relationships where we have a gradient of ecological response to a gradient of flow alteration. So that's, in theory, should be giving us a stronger, more robust sense of the relationship and the points at which we can expect response to really be very pronounced in that relationship between flow alteration and ecological response. Obviously, when we start to bring in data from other places across rivers within a type, we also generate a lot more scatter in the data. There are a lot of complexities around the variability in scatter that we have to handle from a statistical point of view. But essentially, what we start with usually in this process is flow ecology hypotheses. So we start with understanding what do we expect the relationship to be based on our understanding as professional people working in various disciplines within river ecology or within the social science linked to river ecology. What do we expect the relationship to be between flow and ecological response? So we can generate flow ecology hypotheses. So in much the same way as we thought about hydrological data, for ecological data, obviously we want to have ecological measures that are responsive or potentially sensitive to existing or proposed flow alteration. So we can start to pick up what those responses are and then set flow standards to avoid some of the levels of change that we might be trying to anticipate. So there needs to be sensitivity as much as possible. It really is ideal if at least some of those ecological measures can be monitored, because if you recall, it's an adaptive process. The only way we're going to know if our environmental flow standards are working is to be able to monitor it and check and refine those recommendations. We have to be able to monitor and validate with monitoring data. And ideally, we want some measures that are valued by society. And here are a number of examples. For example, aquatic invertebrate richness might be very sensitive to flow alteration in the particular basin we're considering. Larval fish abundance might be particularly relevant from a social perspective because fisheries is a key ecosystem service provided by rivers of a certain type. So we're looking for metrics for the individual river types that can be meeting one or more of these criteria. So how do we think about the conceptual relationships, the hypotheses between flow and ecology? And here's an example. This is a hypothesis we might expect an invertebrate ecologist to put on the table. Their expectation might be that there's a very clear relationship between the frequency of small floods and the abundance or biomass of invertebrates in a particular river type. And much of the literature tends to support this with invertebrate communities in different types of systems. So, for example, as we increase the frequency of small floods, we can expect there to be, if we think about invertebrate abundance overall, we can expect there to be a decrease in abundance. As small floods increase, the substrata materials in the river bottom are being moved around more, and invertebrates are responding to that and moving into the riverbed or drifting downstream. So they're responding to the small floods, and we'd expect over time, as the frequency of those small floods increase, that we'd eventually start to have a reduced abundance. Similarly, if we have fewer, we have a lower frequency of small floods. So small floods are occurring less often in the system. We could also similarly expect a relationship in the other direction in this case. And the reason being, as our number of small floods, our frequency of small floods decrease, those small floods have a very important functional role in this particular river, in this particular basin, and that is in moving the fine material, mobilizing it and transporting it out of the system so that the interstitial spaces between the cobblestones of the river are in a good condition and free of sediment, and that's very important for maintaining populations of invertebrates. They have living space between the stones. So as we decrease the frequency of small floods, we can expect decrease in abundance because that living space is being lost. So that would be a hypothetical flow ecology relationship. There are no empirical data points on this relationship. This is best professional understanding of what we can expect the response to be between this measure of hydrology and its alteration and this measure of invertebrate response. So we can really develop these relationships in any basin where we have people working on the ground who actually know something about river function, river processes, social dependencies of people on those processes. We can start to build up these flow ecology conceptual relationships. And this is an example from the Magdalena-Cauca Basin in Colombia for a particular river type. This is if you remember, they were the very variable high altitude grassland streams of the Páramo river type. For that type, we were able to develop with experts in an expert workshop process a number of different anticipated flow ecology relationships and flow alteration ecological response relationships. And I just illustrated a number of those here. For different, on the y-axis are different indices, different ecological measures, whether it's the richness of invertebrates or it's the biomass of periphyton on the stones, or it's the relationship between, the ratio between fine and coarse scale material, sedimentary material, different kinds of ecological measures, and different, on the x-axis, different flow measures, which are known to be very good at linking to the ecological response. So we can build out these flow ecology, alteration, ecological response relationships. And for the whole of this river system, for those 11 types, ecologists were able to derive, and social anthropologists as well, able to derive about 56 potential flow ecology relationships that could be used in setting environmental flow standards. Of course, some of these they felt very confident about. They felt that they really believed that these relationships were, existed and that they could describe the actual shape of the response curve. In others, they were a lot less confident, and so one could screen out the stronger or more robust relationships. One can then go on to look at collecting ecological data, seeing what ecological data exists to support those flow ecology hypotheses. This is an example of empirical data from a stream basin in Arizona. In this case, the measures are actually the cover of plant species along the wetted channels of the rivers in relation to the flow index of flow permanence. And I'll just highlight one example, but you can see the relationships are very different for different species along the river corridors. In this case, if we look at the hardstem bulrush in the top corner, we can see that there's a very distinct relationship between flow alteration and ecological response. So the hydrological variable is annual flow permanence as a percentage. And on the y-axis is the percentage cover of hardstem bulrush. You can see that whether it's wet season or dry season, whichever time of year we're looking at this plant as an indicator in terms of the degree to which it's covering the wetted areas of the banks, that unless there's permanent flow, it's not there. It's not present. The cover is negligible. It's only when we have permanently flowing systems that this plant is there in varying percentages of abundance according to which stream we're looking at. So you can see a very distinct threshold, abrupt threshold relationship. It's either there when there's full flow. As soon as we start to reduce flow permanence through alteration of some kind, we can expect it to not be there anymore. Some of the other plants actually may be favored by decreasing permanence of flow, and they actually increase as there's alteration. So they're good indicators of alteration, but from a very different perspective. And so we can see very different relationships. Similarly, in this example that was used, actually this example has been used to set environmental flow standards in Massachusetts in the US. And there they had, at the scale of the whole state, they had really good information from different monitoring locations on hydrology, but they also had very good information on different kinds of fish species. They were able to develop relationships between the abundance of certain fish species and measures of hydrologic alteration. And the most useful measure that they found was the percentage alteration of the August median flows. So that was, I think, as I gather, that's a very dry month of the year, naturally a low flow month. And depending on how much that low flow is altered with withdrawals of water for irrigation or for other uses, they found some very clear relationships with groups of different fish species. And they were able to then develop those empirical relationships using this existing data from across different parts of the state. Going back to Magdalena, if you recall, our relationships were conceptual. How would we populate them empirically? They were challenged in a very data-poor situation. There isn't very much information for some of these river types. So in some places, the relationships remain purely conceptual. And the idea is then to go out and really do targeted data collection to start to really refine those relationships with empirical information, where time and data and resources allow that to be possible. This is an interesting example because for one of the river types, we actually, for one of the flow ecology relationships, we did actually have information, very little information, as you can see, three little data points, but with fairly strong relationship, very good relationship, for another Páramo river, the Guataquilla, not in the same basin, but also high altitude Páramo within the same country. And so one can start to think about bringing ecological information in from appropriate places elsewhere. I mean, obviously when one extrapolates, one has to be very careful about how that's done. But in this case, the experts there felt very confident. The system behaves in the same way. The hydrological behavior is very similar. And so we're able to at least bring in some idea of the same flow index and the response of basic invertebrates from another river for which environmental flow determination has been done within the same country and the same kind of biome and under the same habitat conditions. So one can actually use other sources of information in this way. So that's really something about the science process. The fundamental difference is that we've moved from individual sites with a longer stream segment to thinking about, by river type across a gradient of response and a gradient of alteration. That's really the essential thing to bear in mind when you think about the difference in the approach. So when we move on to thinking about social process, we have to think about it in very much the same way. And I have to say that this is a relatively undeveloped part of the framework at the moment. If you bear in mind that this framework was published internationally in 2010, so it's, although some elements of the process have been around for longer than that, the entire framework operating as such has really only been out there for testing and application for a very short period of time. And the social process is definitely lagging at the moment. So, we're encouraged by social scientists actually exploring how to really make the social part of this process more robust and more appropriate for the scale of environmental flow assessment. Well, we can think it's in the same way as we might across a river or a river and a number of tributaries. We can think about understanding what is the ecological acceptable condition for the system to be in. So we might be using ecological goal classes. These are some examples from the US where we have different classes of condition for rivers. And we could think about, we may have, for example, in Connecticut they have 4 classes. Natural, class 1 rivers are in a natural condition, and they may be, of course, spread across the state of Connecticut in different places. Class 2, very near natural. Class 3, they're kind of moderately effective, but they're doing okay, they're fairly healthy. And then class 4, they're not considered in an ecological healthy state. So they have 4 classes of rivers across the state of Connecticut. Similarly, Maine has a 4-level classification. Mexico has a classification that's just been published. We developed a classification. There was no classification for Mexico in existence when the environmental flow, to help with environmental flows. We developed a classification based on ecological importance combined with water use pressure and importance. So the importance of any one river in the basin from an ecological and social perspective, and from a water use perspective in terms of its importance as a water resource in the present or in the future. So a very simple classification based on those two factors. South Africa has another very different classification that you may or may not have come across in materials and so on. And we could think about, we might have river types classified. We may want all river types. We may want all the rivers in type A to be in excellent condition because they're the water tower streams of our basin. We may accept that we need 70% of the rivers of that type to be in excellent condition. We may be able to accept a number of those to be in a class 2 condition, near natural, slightly altered. And we may have may want to think about setting different classes of condition for different river types, and then monitoring on the ground at the control points whether we're attaining and keeping those rivers in those classes. The important thing to think about is that this process is not it's not the scientists who decide what condition the rivers or the river type should be in. It's the stakeholders in the basin that make that decision along with the decision maker. So they have a discussion, a vision, that they agree on what kinds of condition, what levels of health they want rivers to be in the future. And then the environmental flow standards are set to meet those conditions of health. So how do we set the environmental flow standards? Of course, we've developed the flow ecology, flow alteration, ecological response relationships. We've got the classification and all of those steps. But how do we set standards? And setting those standards, it's essentially in terms of acceptable departures from natural or from baseline. I mean, how much alteration is acceptable from a societal perspective for a certain type of river or a certain control point within the basin. And that's really, again, the society makes that informed decision using the information that ecologists and social scientists provide. So it's not a decision that's taken within the science by the scientists themselves. And I'm going to just give a number of examples in the literature, and you can certainly have a look at all those kinds of examples. I just wanted to talk through one very simple example. It's a good one because it's gone all the way from the classification right through to an online water withdrawal permitting tool. So it's now they've now taken environmental flow standards and used them for permitting processes for water withdrawals. So it's a nice example to illustrate how one can use environmental flow standards for a certain type of river. And this is the Michigan Water Withdrawal Assessment Tool. So just the specifics of this are published and people can read up about it, but essentially on the x-axis they have the index of flow alteration. In this case it's the median August base flow, which was a very sensitive flow measure in relation to ecological response. And on the y-axis they've got ecological condition using, and they've got two flow alteration ecological response relationships, a pale grey one and a black line. Those are two response relationships for two very different groups of fish species. One set of species that have a much narrower tolerance range and habitat range than the other. So they have some specialist species, one might think of them as specialist species, and they have some more generalist species in very simple terms. They have the actual characterization percentages is a little bit more complicated. It's not necessary to really understand the details here, just to know that there were two very different groups of species, two different relationships that they used together, and there was different degrees of sensitivity across those two response curves for those different groups, different sensitivities to this measure of flow on the x-axis. And so they had a discussion, they developed through the science process the flow ecology response relationships, flow alteration, ecological response curves that they felt were the best curves to use, and they stayed with one kind of curve, one set of curves based on fish. They didn't use other components of the ecosystem, but they could have used, for example, riparian vegetation if they'd had similarly good data on that. And they felt most confident in using fish information. And there was a discussion with the stakeholders who came to the point of view that the 10% change, 10% reduction in ecological health was an acceptable degree of change for the rivers in this basin, and they felt that that was an acceptable degree of change across all the river types within the basin. And so one can look at a 10% change. What would that mean for these two curves, these two response curves? Well, the sensitive specialist species curve would start to show a response around this point, whereas the more generalist, more tolerant, perhaps, special sandwich would show response a bit later on. Let's start to think about those points of response as being management, as triggering certain management actions. So, for example, we consider that this 10% reduction, that means a change of this much. That means one could alter the flow based on this measure of flow by this much, and you would start to get what's still considered by stakeholders to be an acceptable level of impact on the resource, on the river system of this time. When you started to, with that 10%, if you took 10% of the other response relationship, that meant you could take more flow off. But when you went beyond that, when you took more than this percentage of flow off at this particular location, this particular control point, when you started to move into this much alteration, they considered you to be moving into an area of adverse resource impact. And there would be different management actions that would be triggered as you moved further and further along this gradient of alteration. A couple of interesting things to bear in mind about that is firstly, obviously, although they use the same fish flow alteration ecological response relationships, the nature of those curves will be different for all the different flow types within the basin. So they had classified, if you remember, their different river types, a number of stream types, small warm water streams, cold small rivers, and so on. They set the same degrees of acceptable departure from natural condition for all of those stream types, but as you can see, the relationships between alteration and ecological response, we can expect those relationships to look different in these different streams. As a result, the percentage of water that can be taken off, or the percentage of alteration that can happen, will differ by stream type. Even though the stakeholders agreed a 10% change was acceptable, it will mean different things in terms of amount of permissible alteration for each of these types, right? So think about it that way. And the interesting thing is this approach has become a licensed tool, an online tool. It went through the courts, and the law, when it was reviewed and legally reviewed, the agreement was that to take it from 10% to only 3%. So far more precautionary percentage change was actually allowed legally and gazetted as legally allowed than was originally even recommended by stakeholders. So they went for even more precautionary protective approach at first. And when one can go online within the state of Michigan into the system, and if you're wanting to get licensing for withdrawal of water, you type in where you are in the river basin, and it will use, in the background, it is using these relationships to see where already cumulatively alteration is for that river type in that place in the basin. So using that Hydrologic Foundation for decision support, it's really saying, well, for this it is a cold stream that the withdrawal is taking place on. We know we're already in this area of withdrawal based on the existing permit applications. So you're getting very close to this adverse impact line. We're going to recommend that we do further studies before giving you a permit. Or they could say, well, you're well within the acceptable resource alteration state, permit is granted automatically online. So that's where they've really taken the flow standards and used them as a regulatory tool for water management. And there are a number of different ways in which these environmental flow standards have been translated into rules or have supported regulatory and licensing frameworks. There are a number of examples one can look at. This is just a nice example, one that's gone all the way through. And so one can see it in table form. It might look something like this: the same relationship with the ecological stream types, and there are these water withdrawal management zones. Different zones, different degrees of alteration, and as you get to zone B, adverse resource impact. In the cold streams, once you go beyond 20% alteration, you're in that adverse resource impact zone. And so that really becomes a screening tool for water resource management. That's just a first run through the ELOHA framework. It is quite tough to explain it. I think it's good to go back and read the original paper, the 2010 paper, which this is based. There's also a really great set of tools online. There's an ELOHA toolbox. You can go in and look around in that toolbox and get examples. And there's also a very recent publication that should be out shortly, which looks at all the different ways in which ELOHA has been applied in the US, specifically, which is where this tool has first been applied. It has also been applied in Australia, and as I showed you, it's underway in application in Latin America. But in terms of going the full cycle to full implementation, the United States has some very good examples. So you can have a look online. There is also some good reading material on classification, ways in which the classification process has been used to identify the different types of rivers and streams within these large geographic areas.